Hello, so we are going to discuss today is the series RLC circuit. So let us say we are driving this circuit with the input voltage source V in of t. Let's draw it properly. And this is a resistor R, inductance L, and capacitor C. The current that flows through this circuit is I of t, right? And this is a series RLC circuit. All right. So now if you want to calculate the impedance of this circuit, it is nothing but the ratio of voltage over the current, which is V in of t divided by I in of t. Fine. And Z of t can be given as a series combination of these three components right here. These are all in series. So we can write that Z of t is resistance of a resistor plus XL is the inductive reactance or impedance plus XC is the capacitive inductance or impedance. And in the S domain, what we write it would be Z of S, that would be then R plus XL would be written as S times L plus XC would be written as 1 over S times C. Okay, so this is how we can write here, where we see that XL is S times L and XC is 1 over C times S. So that's the impedances for the inductor and the capacitors respectively. So we now put S equal to j omega, and therefore this equation takes the form as shown over here, R plus j omega L plus 1 over j omega C. We can further simplify it, R plus j omega L. This term can be written as minus 1 over j omega C, right? Not really. It can be written as minus of j 1 into 1 over omega C. So 1 over j can be written as minus j here. And then we write R plus, we can take the j common, omega L minus 1 by omega C. Fine. So we have this expression for the Z of j omega, that is our impedance of RLC circuit, series RLC circuit. So what we see here, we can calculate the magnitude of this equation. So magnitude would be Z of j omega. It would be square root of the real part. So remember, the real part is R and imaginary part is this term. So we can write R square plus omega L minus 1 by omega C whole square. So that's your magnitude, right? And angle of Z omega would be written as tangent inverse of this term, imaginary part divided by the real part. Right. So we now can have several cases to plot the magnitude with respect to frequency and the phase with respect to frequency. So for the first case, let's say omega is equal to 0. In that case, Z of j omega will take the form of R square plus omega L. Omega is 0 now. So 0 minus 1 by 0 whole square, right? We can see that what value it takes. So it would be R square plus 0 minus infinity whole square, which would be written as r square plus minus infinity whole square, be written as so it is infinity. So for the omega is equal to 0, this value is infinity. And the angle in that case will be z of j omega tan inverse of 0 minus 1 by 0 will be tangent inverse of 0 minus infinity. It will be tan inverse of minus infinity. Be minus tan inverse of infinity would be minus 90 degree. Fine. So if we want to plot this right here, we can see that, let's say this is our magnitude z of j omega. This is how the magnitude looks like. And here we have a omega axis. Omega tends to infinity, omega is equal to 0 right here. And somewhere here we can plot angle of the impedance with respect to frequency. So at omega is equal to 0, this plot starts with the infinity, a very high gain somewhere here. So the gain is very high. The impedance is very high, right? We can say that this is approximately infinite, this value right here. Or let's say the impedance is very high, okay? Approximately. And the phase is minus 90 degree right here. And then it will see how the phase and the magnitude of both these terms will vary. Okay. Now for the second case, we come back here. For omega is equal to, let's say, omega L is equal to 1 or omega C. So if that is the case, we see that z of j omega, let's write it properly, would take the form of r square plus this omega L is equal to omega C. So this term becomes 0 now. We see that this term right over here, we are saying this term because these two frequencies are same. So that's the 0. And therefore, what we see, the magnitude has a value of r. And the angle z of j omega would be tangent inverse of 0, right? It would be then 0. So for the case, we see that we can draw the magnitude is r somewhere. Let's say here the value is the r, and at that frequency the phase takes the form of 0 degree right here. So we see that, and this frequency is when omega L is equal to 1 over omega C. So these two frequencies are matched. And now we see that for omega is equal to infinity, z of j omega would be square root r square plus infinity minus 1 over infinity whole square. So we are again referring back to this equation right here. Okay, so it's infinity minus 1 over infinity whole square. And if we try to solve this, what we have here, this r square plus 1 by 0 whole square would be then r square plus infinity square. Then it's again infinity, right? And the angle z of j omega would be tangent inverse of infinity minus 1 over infinity divided by r, and it takes the form of tangent inverse of infinity minus 0 divided by r, which is tangent inverse of infinity. Finally, it is plus 90 degree. So we can refer back to figure and we see that the phase is going to plus 90 degree when the frequency is very, very large and the magnitude is going to infinite. Okay, so that's how the impedance plot looks like. So this, you can see that this is the response of band stop filter. Actually, if you look at the impedance point of view, the impedance response looks like a band stop. Within a certain frequency range, the frequencies are blocked, and outside the frequencies right here and right here, this is a pass band for these impedance spectrum. Okay, we can have some other conditions. For instance, let's say other conditions. For instance, if we say that if omega is equal to omega L is very, very greater than omega C. So in that case, we can approximate the magnitude and phase function like this. So it would be R square plus omega L whole square, because omega C, 1 over omega C can be neglected in this case. And the angle Z of j omega would be then tangent inverse of omega L divided by R. Similarly, for the case omega L is very, very less than omega C, we can write Z of j omega would be R square plus minus 1 by omega C whole square. So we can say that we have this, and angle would be Z of j omega tan inverse of minus 1 over omega C divided by R. So that's how we see these things will takes place for the impedance plot. So this is, let's say this is case 1 and this is case 2. So for the case 1, the final value of the magnitude, if we calculate the magnitude, it is going to be R square plus omega 0 square, because in this case omega L is equal to 0, right? And omega L is very, very greater than omega C, 1 over omega C. So therefore we can see that the impedance takes the value of R, and the angle Z of j omega would be tangent inverse of omega L is 0 now divided by R. So it is going to take the phase value is 0 degree. Similarly, we can solve for case 2. Fine. Now let's focus upon the admittance. What is admittance? So admittance is Y of S. It is the inverse of Z of S. So it's the inverse of the impedance. So we know that the impedance is R plus LS plus 1 over CS. Therefore, Y of S would be 1 over Z of S would be 1 over R plus LS plus 1 over CS. So this is how we can get the values. So we put S equal to j omega in this above expression. The admittance takes the form now 1 over j of j omega. So it takes the final value R plus j omega L minus 1 over j omega C. We've solved this for the impedance case. So this can further be simplified as R plus j omega. Let's say j is outside, omega L minus 1 over omega C. Okay, and so this is the expression for the admittance. So let's get the value of admittance, magnitude of the admittance. So it would be square root of R square plus omega L minus 1 by omega C whole square. And remember, we are taking the admittance, so it's the inverse of the impedance. So magnitude of the numerator would be 1 and magnitude of the denominator would be this term. So this is the magnitude. What about the phase plot? Angle of y of j omega would be 1 over angle of 1 over z of j omega. So it would be 0, phase of the numerator, right, in this term, divided by, so phase of the numerator is 0 and the phase of the denominator. So 0 is the phase of the numerator minus phase of the denominator would be written as omega L minus 1 over omega C divided by R. So this is for the phase. So we got these two expressions for the admittance. And now what about we try to plot the response of the admittance with respect to frequency. We plot both the terms, magnitude as well as the phase with respect to frequencies. So let's have that plot ready and we see how it looks like. So let us say this is y of j omega magnitude, and here angle of y of j omega. And this axis is our frequency. This axis is our frequency, which is omega rad per second, angular frequency. Omega is the angular frequency. So we come back here. For omega is equal to 0, when frequency is 0, the magnitude y of j omega would be given as, let's go back to expression. This is the expression we have. So it is 1 over r square. We just see that 1 divided by 0 minus 1 over 0 whole square can be solved as r square plus 0 minus infinity whole square 1 over square root of r square plus minus infinity whole square. So 1 divided by infinity. So it is 0. So we see that for the case omega is equal to 0, the admittance is 0, and the angle y of j omega would be, right, this is the expression for the angle we see here. Okay, so we plug in the values. So it is 0 minus 0 minus tan inverse of 0 minus infinity, or with 0 minus tangent inverse minus infinity by r. So it will be tan inverse of infinity. It will be plus 90 degree. Fine. So we start plotting the graph. So magnitude of the admittance is 0 when omega is 0, somewhere here omega is equal to 0, and the plot and the phase is plus 90. So let's say this is plus 90 degree at omega is equal to 0. Okay, next is same value. Let's say when omega L is equal to omega 1 over omega C. So in that case, we can again see that how the response looks like. So this term in the denominator is now 0, and we see that the admittance is has a finite value given by the value of a resistance, value of a resistor. So it would take the value of R. So somewhere here we see that the plot goes like this, and the admittance takes the value right here, which is R. What about the phase? Phase is y of j omega would be 0 minus tangent inverse of 0 divided by R, and we see that the phase is 0. So we come back here to draw the plot somewhere here. You see here, and the phase is dropping to 0. So let's say here we have a 0 degree. What about the third case? When omega is infinity, so magnitude will take the value of 1 over square root of r square plus infinity minus 1 over infinity whole square. This is how, after plugging the values, the expression looks like. So it's going to take the value plus 0 whole square r square plus infinity whole square, and again it looks like this magnitude 1 over infinity is 0. So we can plot this, and so when omega is very large, the magnitude is dropping to 0 right here. What about the phase? We try to solve for the phase. We see that it is 0 minus tangent inverse of infinity minus 1 over infinity divided by R minus tangent inverse. Well, here we made a mistake. Has to be 1 over infinity is 0, so it's gonna be minus 90 actually. So we see here phase is shaping from plus 90 to 0 to minus 90 right here. So this spectrum looks exactly opposite to the impedance plot. So this is the function of a band pass filter. We see that this is band pass filter response when we try to plot the admittance of the series RLC circuit. And if we try to plot the impedance of a series RLC circuit, impedance is the inverse of the admittance, or admittance is the inverse of the impedance. So they are opposite to each other. So while the phase shift for the impedance plot is from minus 90, it goes through 0 to the plus 90, we see that the phase shift for the admittance is the opposite of the impedance. So it goes from plus 90, passes through 0 and approaches minus 90. What about the magnitude? At omega is equal to 0, admittance is 0, it increases, takes the finite value of R at middle frequencies where omega L is equal to omega C. And one thing we have to note here, that omega L is equal to 1 over omega C. We have taken this approximation, right? So the frequency at which this peak is attained is called as a resonant frequencies. Resonant frequency. And the value of the resonant frequency, omega R, is given as 1 over square root of L times C. So that's the frequency. So we see that this band pass function is opposite of this band stop. So impedance drops to 0 at this frequency, but the admittance at this frequency takes the value of a finite value of R resistance right here. So that's how these two plots look like. Fine. So once we have that, done, what about we try to obtain the transfer function of the voltages instead of impedance and the admittance. So let us redraw the circuit right here. So let's say we have an inductance, then a capacitor, and we shunt put the resistor right in this fashion. It is again the series RLC circuit. We have the input driving source V in of t, and we close the circuit right here. And the current that flows through the circuit is R of t. Fine. And what we do here now, we try to obtain the voltage VO of t across the value of this resistor right here. So the transfer function is the ratio of VO of t divided by V in of t. We know that. So how to obtain the transfer function and plot it with respect to frequency. So let's try to apply the voltage division rule. So we can write VO of t is nothing but we use the resistance divider. This is our inductance actually. So we correct there, and this is capacitor. So what we do here is the R times V in of t, we are applying the voltage division rule, where in the denominator we have R plus XL plus XC. So again, XL is the inductive reactance or impedance, and XC is the capacitive reactance or impedance. So in the S domain, we can write VO of S that equals to R in times V in of S divided by R plus J omega L. Not J omega yet, SL plus 1 over SC. And now we put S equal to J omega in the above expression. So this takes the form R times V in of J omega divided by R plus J omega L plus 1 over J omega C. We can further solve it like this. We can take the ratio of two voltages, which is what we want at the end. So J omega L minus 1 over omega C. This is how we can see that final expression looks like. So let's call it the function A. The magnitude of A is nothing but the magnitude of these two right here, okay? Let's call it A. So that's the magnitude of the voltage. And if we want to obtain the A, which is this one, so it would be given as R divided by square root of R square plus omega L minus 1 over omega C whole square. And the angle in that case, angle of A would be 0 minus tangent inverse of omega L minus 1 over omega C divided by R. So that's the expression for magnitude. That's the expression for the phase angle. for this circuit. So we are trying to obtain the voltage across the resistor. We can also have the voltage across the capacitor or voltage across the inductor. We can also have the current through the circuit. Current is going to be the same through all these components. So that's how we can manipulate the variables here and obtain the expressions. So now once we obtain this, so let's obtain the response of the output voltage at these frequencies. So at omega equal to 0, what the magnitude will take, let us focus on this expression. It would look like R divided by R square plus 0 minus 1 over 0 whole square. And this takes the value of 0 as we can derive it. And the angle would be 0 minus tangent inverse of 0 minus 1 over 0, and it takes the value of divided by R. So if we solve it, it takes the value of plus 90 degree. So for the omega is equal to infinity, we see that the gain will take the value of R square plus 0 infinity minus 1 over infinity whole square. If we solve it as before, the way we solved it for impedance and the admittance, we can also solve this for this voltage. So this takes the value of 0 and the angle takes the form like this. And we see that the angle would be 0 degree. What about the angle would be minus 90 degree, not 0 degree actually. If we solve it, you can solve it yourself and see that it takes the value of minus 90 degree. And at the frequency when omega, for omega is L equal to 1 over omega c, the magnitude is R divided by square root of R square, and the term here takes the value of 0. And if we solve it, it takes the value of 1. And the angle would be 0. All right, so we have obtained it for all these frequencies, and we now try to plot it. So the plot will look like this. So let's plot this. So this is your magnitude, and somewhere here it's a phase. This axis is your omega. This axis right here is your omega. And we see that at omega is equal to 0, the magnitude is 0. And at omega is equal to 1 over omega c, the value is 1, like this. And then as omega approaches infinite, magnitude again falls to 0. So this is basically VO of t divided by Vin of t. Okay, that's the magnitude plot. And the phase at omega is equal to 0, phase transitions from plus 90, it passes through 0 at the middle frequency and approaches minus 90, as we've seen that. So this is your plus 90 degree, this is your 0 degree, and that's your minus 90 degree. All right, so we've solved this, and remember we have this resonant frequency omega r, which is given by 1 over square root of LC. And at the resonant frequency where inductive frequency due to inductive impedance and the capacitive impedance, they both match to each other, is called the resonant frequency and is given by this expression. and the angle at this frequency, that is phi or phi, let's say phi is 0 degree. So at resonance, the phase is 0 as pointed here. So we see that we have plotted impedance versus frequency, admittance versus frequency, and the output of these circuit versus frequency, both magnitude and the phase. But how do we verify it? Actually, these values for the magnitudes and the phase, are they matching to what we have calculated? We can do that. We can actually use the spice circuit. Let's see right here. So we see here we have the series RLC circuit. Inductance has a value of 1 Henry, resistance is 1 ohm, and capacitor, let's say 1 farad. And what we do is that we have a voltage source here, the AC voltage source, and we have set the value of it to be 1 volt. And what we do is that we run the AC analysis. As we see that from here, we take the sweep, type of sweep to be decade, and number of points thousands. We start with the zero frequency. We can't start with the zero frequency in spice. So what we do is the very low frequencies near to zero, 1 millihertz, 1 millihertz I said, and up to, let's say we have 1000 megahertz frequency response to be plotted. So once we do that, we run this analysis, we can run this, and we have simulated the response right here. So let's focus first in the bottom plot. So before that, let us take a look at the current direction. So you see in the red arrow in the schematic, it points towards the right. So it shows the current flow direction through the inductor. There is the current flow direction through the resistor, and the current flow direction through the capacitance. So the conventional current is flowing from right to the left through this loop right here. It comes from the positive terminal of these voltage source and then passes through all these components, and it closes the loop and enters into the negative terminal of these voltage source. But take a look at here. If we point at the voltage source, the current flow direction is from positive to negative. So, which is what we just understood. So SPICE actually computes it in a reverse direction. Okay, so we have, when we plot the results, we have to take the negative of the current, right? So SPICE shows that it is entering from positive to negative actually. Okay, so look at this graph in the bottom here. What we have plotted is the voltage divided by the current, negative of the current. It just for the fact that we explained here, the direction of the current is negative, just to match with the theoretical results, because SPICE does the opposite. In the SPICE, the direction of current is opposite to what we conventionally took. Okay, so we see that as the frequency is 0, the impedance is 40 dB, which is very high. So theoretically, we had it infinite. And then at some frequency, the resonant frequency is about 100 millihertz, which is 1 over square root of LC. If we calculate that, it's about 0.1 hertz. So impedance has a value of 0 dB, approximately 0 dB. So it is about 1, which is the value of a resistor in the simulation. The value of resistor is 1 ohm here. And as the omega approaches infinity right here, the impedance is approaching infinity. What about the phase? So we had the phase calculation. It starts from -90 at resonance. It takes the value of 0 degree, and at omega equal to infinity, it goes to +90. So the phase transition is from -90 to +90. So let us verify that in the theoretical way, in the theory, whether we said is matching or not. So we can come back to plot of impedance here. So we see that the impedance plot right here for the magnitude looks what we simulated, and the phase is from -90 to +90. So yes, it's matching with what we computed. What about the admittance? So this is the plot of admittance. So see that at omega is equal to 0, admittance is 0, and at resonant frequency, it takes the value of R. R is 1 ohm in the simulation. So it's 0 dB or 1, and then it goes to 0. Phase transition is from +90 to -90. It passes through 0. So let's verify that. So this plot in the middle in the blue is the ratio of current divided by voltage, which is the admittance. And again, we have plotted the negative of the current just to match with our conventional, because SPICE does the opposite thing. It plots the current value as a negative of what we simulate. So we see that admittance plot looks like what we calculated in the theory. At omega, at the resonant frequency, it has a value of 0, and it has a value of 0 dB, which is 1 in magnitude. And at omega equal to 0 and omega equal to infinite, the admittance is approaching 0. And what about the phase? Phase is +90 to -90. So what we calculated in theory. Okay, finally, let's take a look at this one. So this is the difference between the two node voltages divided by input voltage, that is VNO01 minus VNO02. So that is nothing but the voltage drop across this resistor. So we are trying to, in theory, remember we calculated the voltage drop across the resistor and divided by the value of the AC voltage Vin. So that's what this plot is about. So again, at resonance, it has a value of 1, and at omega equal to 0 or omega equal to infinity, so it's a value magnitude is 0. So it's a band pass filter, and the phase transition again is from +90 to the -90. At resonance, the phase is 0 degree. So let's see if it's matching with the theory. So look at this plot here. This is our plot for this circuit. The circuit is this one, right? So we are trying to obtain the voltage across the resistor, which is output voltage, and dividing it by the input voltage, which is set to 1 volt in the simulation. So it's the transfer function. That is what we are plotting here, right? So let us take a look. Yes, the value of this bandpass filter gain at resonance is 1, and phase transition is from +90 to -90, and at the resonance the phase is 0 degree. So this is how we calculated the theoretical values for these magnitude and the phase for the series RLC circuit for 3 different parameters such as impedance, admittance, and the voltage transfer function. And to verify these calculations, we use the SPICE simulation software. As we see here, we set up the components with their values. We set the voltage AC voltage source with the value we set equal to 1, and then we run the AC analysis to obtain the frequency response as shown over here. And we verified the theory with the simulation. So all right, so that's how we can analyze the frequency response of any circuit. For instance, we analyze the frequency response of series RLC circuit. Yeah. So it's a passive circuit. So we see that the gain is equal to maximum gain that we have is 1. So upper 2 plots are the voltage transfer ratio or the admittance respectively, and the bottom plot in the green here is the admittance plot.